you get socks, and then you walk in the bathroom, and there's a little bit of water on the floor, and then your socks are wet. And this is terrible. And one day, I'm gonna have a robot in my house, and it's gonna mop the floor whenever I get water, and this will never happen again. Like, think about it. Home robotics, but it goes in the bathroom, and it always just takes a paper towel and, cleans up that floor after you. That'd be nice. That'd be nice. Good morning, Twitchies. We got something today. All right. You know how I like the idea of a superscalar, and I was like, oh, I'll make a great RISC-V processor. Well, that sounds hard. What if instead we do things that are easy? What do you guys think? Does that sound like a good plan? So you end up back in bullshit land. You start working on this for a bit. And then, we'll wait for some people to get in here, and I can tell you guys what I realized. All right. Look, as much as I'd like to make a great RISC-V superscalar processor, is that really where my strengths are? See, why does Grok have a stupid wide, did the memory issue get solved? Not really. I just realized that a lot of my strides were 1. Like, we just wrote the reduce ops, and they all have strides of 1. And we're getting good utilization on this thing. Okay, so maybe first I'll show you guys what FNEED is. So all my tests are passing now in TinyGrad. I wrote the reduce ops. The only thing that I haven't written yet is the backwards convolution. I'm just, it's just painful. But all the forward pass now of EfficientNet is being done on Cherry. Here's a fun thing for somebody to do. You don't even have to use Cherry for this. Can somebody just write ResNet 50? Can somebody write ResNet 50 in TinyGrad and also get me BERT large? We need ResNet 50 and we need BERT large. And then, all right, so I know I'm what I railed against about all these people wanting to push all the complexity to software, but I kind of already have all the software written. Like there'll be bullshit importing it to PyTorch, but it just makes my life a lot. Like I think about, okay, am I actually capable of building a high performance superscalar processor? Like, at some point you got to be honest with yourself and kind of say, no, probably not. Like, could I, if I hired people and stuff? Maybe, but what if, like, I don't want to hire anybody and I just want to build my own AI accelerator, right? So what can we actually build? And like, because whenever you think you're going to hire someone to do something, it's always because you don't really understand how to do it. You know what? Cherry pivots so quickly. I wasn't even, you know what? Like, let's be honest. Let's be honest here. Let's take a look at, you guys all watched me code up RISC. You guys watched me code this CPU. This CPU, I'm sure, is chock full of bugs, like tons of bugs. And I also think that, What? The issues? Yeah. Oh, the tests are not passing. Which test isn't passing? Oh, well, we got a bug. Wow, you got some fancy visualizer software. Uh-oh, which one fails? No, I tested add.hex and it works. But I also got rid of those tests and I changed it to different tests. I didn't understand those tests. I wrote a script to get tests. Where's my get test script? Did I not commit it? Oh, I didn't commit it. Oh, yeah. Oh no. Get tests. All right, I added something to get the tests and to make hex, and then you can simulate, and it should work. Wait, you added more stuff? Well, check out the change I made. Oh. Okay, I mean, I guess, I don't know. I don't know why you copied in all the firmwares. Because we just shouldn't have a directory called firmwares. Like I just wrote this script called get tests, which just gets and builds the tests right from the RISC-V repo. So I would just use that instead of like, because we shouldn't be making copies. Like you could add it as a submodule if you want to. I also tried Real to get Linux computer to boot on this thing. But all right, so like, let's be honest. Yeah. Let's copy the Google TPU. No, we're not meditating right now. Right now, you estimate the odds of Cherry Computer to be a successful chip company is 1 in 20. Well, that sounds about right. So if you believe that, and let's say a successful chip company sells for $1 billion, then it sounds like we have a $50 million valuation. We're winning, boys. We are winning, boys. Verified open source RISC test. I did. Regardless, we're not working on the RISC processor today. We're working on TinyGrad today, and we're saying, do we really need a RISC processor? And the answer may be no. The answer, like, okay, you know what? I went to Kama yesterday, and one of the guys there was like, you know, the Google TPUs are actually pretty good. And I'm like, do you know anyone who uses them? He's like, yeah, researchers. And they get free Google Cloud credit? And he's like, yeah. Well, so yeah, that's why they use them, right? But I think we can take some lessons away from the TPU that, okay, like, Cherry's pivoting. Sorry to take you all in on this pivot with me, but you know, I'm glad to have you all along for the ride of Cherry Computer. You know, I'm in a good mood. I'm in a good mood today because the tests pass, you know? When the code works, I'm in a good mood. And when we're like struggling and the code like doesn't work, we're not in a good mood, right? So we run these with Cherry now. This is running it all through like the Cherry instructions, which I've simplified even more. How did that just happen? All right, so this is my like emulator for the Cherry processor. It only has 3 registers. No, what do you mean? No. Cherry's still building a chip. We're still going to build training chips that are 10x faster and cost 10x less. I've been working on an extension to RISC-V. Okay, it won't be an extension to RISC-V anymore. Look, the file's already even deleted. I would only support the TF2 data type. That's true. VLIW doesn't work. Well, so let's make some LIW, right? We'll get rid of the V because, you know, Grok's instructions are an absolute joke. But how big are Google's instructions? 322 bits. I think we can even go a bit smaller than that. but I think that's kind of the right idea. You know what I mean? Like, we can just look at all. Okay. Here's basically what you figure out. And guys, I'm sorry, I got hyped on superscalars because I just learned about them. And I'm like, whoa, superscalars, out of order instructions, this core would be sick. But then you realize what this core is doing, and you're like, you're just burning power. And like, did you not learn the lesson from Thneed? Superscalar on RISC-V is great for general purpose compute, but it's not actually good for AI, Guys, if you can't admit when you've made mistakes, you gotta admit when you've made mistakes. So what mistakes did we make? Like, I think about this complex RISC-V processor, and then I'm almost thinking, okay, like, am I gonna run Linux on the accelerator? And then, have you ever heard the expression, done is better than perfect? Oh, that's a great expression. Done is better than perfect. The mottos of Cherry Computer are RISC architecture is going to change everything, done is better than perfect, and fuck NVIDIA. What do you think? We got some great mottos, except no risk. Because like we don't really have a good. The only reason we insult Google is because we can't get them, and just because you can't reach the grapes doesn't mean the grapes are sour. So let's figure out what Google TPU is doing and let's copy it. And I think it's what we have here. Okay, so there's a big part of Google's TPU that's not open source, and it's called libTPU. They have these XLA instructions, but XLA, I don't want to deal with any of that. We have something better than XLA, and it's called Tiny. Tiny are these 14 instructions, and we've now implemented them all, except for the ConvNet backward pass, and things are running fast. Here, look. You want to train MNIST, and I've done the backwards and forward pass of all this. So this is done. We can now train MNIST on the virtual Cherry processor. But okay, guys, this is exciting. What you realize, okay, so let me show you guys Thneed, and Thneed's an important thing to understand on my AI journey. I've been watching Pokemon, as part of my journey to become Pokemon master. I'll bring you guys on my AI journey, and here's kind of what we figured out. Okay, so if we go in here to Model D, you'll see this thing called Thneed. Now, of course, I wrote absolute bullshit. I wrote Thneed is an SMPE accelerator. I know SMPE is already an accelerator, but sometimes things need to go even faster. It runs the local device and it caches a single model run, then it replays it, but fast. Thneed slices through abstraction layers like a fish. You need a Thneed. Okay, so what Thneed is we have this service in OpenPilot called Model D that runs the model, right? This is Model D. It runs the model. It's just pretty boring. It connects to the camera D, it gets the picture, and it runs the model, right? So when it runs the model, it compiles these OpenCL kernels and then uses things like CLNQ range kernel inside of SNPE, which is Qualcomm's neural network accelerator library. Thneed sits in between user space and kernel space and intercepts all the calls to the GPU command buffer, and then replays them, but 10x faster, using 10x less CPU, right? Because the CPU is doing all this like malloc shit, and like you just don't want to deal with any of it. So you realize that you could make all this stuff work. You don't even need to make the first pass actually. All right, fine, I'm building a compiler, I'm getting rid of my superscaler, I'm not trying to do anything unique and special. You know what, this is why it's way better than NVIDIA. We're just building Google TPUs, but we're not gonna be like Google and not let anybody have them. We're gonna build Google TPUs, but for the people, and not using any TensorFlow crap, using beautiful, clean, tinygrad. Oh. So the TPU doesn't even have I might also be reneging on my promise to build a 2D matrix multiplier. you know, the source said something about matrix multipliers want to be square. And like you look at Tesla's and they built square shit. And like you look at Google's and they built square shit. So we might have to build square shit. Oh, yes. So they have a separate matrix unit and vector unit. What's wrong with superscalar risk? It sounds hard. It sounds complicated. If there's any part of something you're trying to build that you don't fully understand, like, do I know how to build a renaming register file? No. I read those words somewhere, but you know, sometimes you got to be honest with yourself, and you get hyped up on all this complexity. Guys, this is the true lesson. If there's a lesson to take away from this, it's like you can get hyped on dumb shit. You can even hype yourself on dumb shit. But you need somebody to come in and be like, yo, that's dumb shit. But nobody did that. I just did that while I was coding. And you know what did that for me? Laziness, boys. Laziness. I'm gonna tilt the monitor up so you guys can see my face all. Look, I realize that I'm a lazy piece of shit and I don't want to write all that complex stuff. So instead of writing all the complex stuff, we're gonna make it simple. Alright? Like, so we're gonna use VLIW instructions. We're gonna figure out how to take the things that I wrote in TinyGrad and VLIWize them. Yeah, what do y'all think? Getting hyped on over-engineering is an age-old mistake. That's true. I know, RISC-V Superscale would be so cool. But like, what about just copying the TPU? What do y'all think of that? I don't mean copying the TPU. I don't mean that for, you know, I'm not here to infringe anybody's patents or, you know, download anyone's books on LibGen or anything. So let's take a look at what Google has in the TPU. And let's realize that they probably did kind of figure this stuff out, you know. As much as the company sucks, maybe they have smart people still working, even though they are talking about performance per CapEx. What the hell is CapEx? What is that? It's some finance term, isn't it? Yeah, you know, performance per CapEx. Ugh, disgusting. They didn't build beautiful things. I want them to build beautiful things. Because they're beautiful. Oh, TCO is per CapEx. You know, I think what I'm also really trying to say is engineers should run the world. And somehow it's always the same. You know, I don't know if you call them the professional managerial class or the politicians or, you know, whoever they are, this certain other type of person seems to run the world. And like, what did engineers ever do but like make things better? What do these people do? Well, they make things worse. You know, I was rewatching an old video yesterday. I went on some stupid rants. Look, I don't care about like that's, you know, I don't care about like the UBI and dumb shit like that. You know, it's like, it pisses me off now, but like, what really matters is redirecting the fight. Instead of fighting against people, we all are on this shared planet Earth and we're here to fight against nature. Right? We're talking, Alex and I are talking, it's like, how come these people run things? Like, is this gonna change? And have people always felt this way? But I don't want to go off on this tangent. The tangent that I want to go off on is realizing that what we really have to do is, okay, we're just gonna write a simulator. We're gonna figure out exactly the thing. And then, yeah, there's gonna be like built-in addressing registers. We're just gonna build a real, you know, ASIC. We're putting the ass in ASIC, you know? We're putting the ass in ASIC. Putting the ass in ASIC. I like that. Oh, there's another slogan. I love these slogans. Cherry slogan number 4. All right. Putting Matrix multiply unit, accumulators, activation pipeline, activation storage. Oh, yeah, look. They made it simpler. Oh, that one looks shitty. This one looks better. The matrix multiply unit and the vector unit. Oh, vector unit. All right, so their matrix multiply unit is 128 by 128. Yeah, that's even less flops than I was going to do. Engineers are hard asses when it comes to managing people. If you'd hire an engineer and come to, yeah, some normie company, a third of the employees would quit, another third would kill themselves, and the rest would sue you. I don't know, man. I've heard Tesla's a rough place to work, but like you get to build something awesome, and that's the trade-off. You have a choice. Do you want your job to have dignity, or do you want your job to be easy, right? And the people who make the latter choice, let's just, you know. All right, I will tell you about my dream for Fake Job Stadium. If you want a little tangent, I think we deserve a little tangent because we realized something today, which is we're not building a fucking RISC-V superscaler because we don't know how to build that. Done is better than perfect. Like, it just like, while I was writing the TinyGrid thing, while I was struggling to make Max work, I'm like, I'm already writing all this code for the simulator, right? And then I was like, I was gonna rewrite it. I was gonna have to deal with like encoding this in bits. And then like, you know, maybe I shouldn't have gone so far into making fun of the VLIW fuckers, right? Like, let's just take the V out and let's make SLY-W sort of long word instructions, right? You think we should operate on vector or matrix vector? Well, so, okay, their matrix multiply unit. Well, that's the other thing. Like, I was realizing that this vector unit thing makes sense when I was, so I'll show you guys the reduce op I was writing. And then I was like, this is also what made, oh my God, why is my monitor glitching? This is the reduce op. And notice how the reduce op like shows up here. Like this 0 is like part of the matrix, which is weird. And really what I want to do is shove that in the vector unit. All right. Let's put the cog back in Grok. Okay. So let's just more carefully read Google's TPU paper and figure out what we're building. Yo, this thing used to have DDR3 DRAM? Like, that's so crappy. Let's read this paper slowly. Okay. Google deployed several TPU generations since 2015, teaching us lessons that change our views. Semiconductor technology advances unequally. Don't they know about equality? Compiler compatibility trumps binary compatibility, especially for VLIW DSAs. Target total cost of ownership versus initial cost. Support multi-tenancy. What? Is that because you guys want to run multiple networks on one? Deep neural networks grow 1.5x annually. Inference DSAs need air cooling. Yeah, Google water cooled their TPU v3s. Do these kind of systems still have cache? No, they don't have cache. And like vector memory is almost exactly what I ended up converging to, right? So it was kind of a myth that my... Okay, so originally I had this fully addressable memory, but it turns out you can't really build that. Because you're asking for way too many... So I ended up with vector memory where each one of my vectors was with 32. It seems like their vectors are with 128. And like, maybe that works. You know what? We should try it. Actually. I don't have that stupid mask parameter anymore, right? I hate masks. All right. So let's do this is inference with size equals 32. But what if I make size 72%? What if I make size equal to 128? Wow. It's still really good. Oh my god. Wait, did that get more than 4x? Wait, it was 551 with 32. Oh, so I 4x that, so that's actually 16x. So no, I mean, it's kind of a scam. But, yeah, okay. I kind of like the 32. And then, okay, so what would happen is this matmul instruction would then take 128. Let me just do that. But we'd end up with the same, we'd end up actually with less flops. It doesn't really make sense to have these dense things, like as much as I liked them. So you can effectively think of a matmul as like, actually, wait, let me work that out. No, those things are, no, that doesn't work. Those things are smaller. I don't know. We'll have to rethink. No, it's not actually, okay, that's not right. That's not right. 32 times 32 is 512. It's 124? Wait, it's 124? Okay, never mind. I don't know what I'm saying. Don't listen to me. We're gonna read the TPU. Like, it just seems like all these things I was doing, you just get closer and closer to designing exactly what the TPU is. And then you're like, well, I could put this superscalar thing in front of it, but do we really need it? I mean, we can compile it all statically, and like, yeah, you know, I guess the thing that's really upsetting to me about the whole space is that despite all these people working, nobody has showed up on MLPerf. Right? Oh, I didn't actually push the website yet. But the only things on MLPerf are NVIDIA, Google TPU, and the Huawei Ascend 910. And that's there because the Chinese were like, what if NVIDIA stops selling us chips? What do you say? You say starts a chip company amidst a chip shortage. We're going to make our own chips. We're going to make them in kitchens, man. I know this kid. And then you realize what you really want to do. What Cherry Computer should really do is raise money and hire like Team Rocket, but a competent version of Team Rocket, to steal the plans for Google's TPUs and just make them. Like, you know, the Chinese already stole them. You like the Team Rocket idea? Oh, you made a logo. Oh, nice. Wait, this is, and you're assigning me the copyright to this logo? Thank you. Look, we have proof right here. Thank you, Brian Wiz. You shall be remembered forever as the person who made Cherry SVG. And by SVG, I mean, why is it a JPEG? Why is it not a SVG? But you know what? Beggars can't be choosers. There we go. There's your logo right there. Pretty big, yeah. Oh, beautiful. You'll upload the SVG, thank you. All right, so we're gonna read this paper slowly. I know it's 2021. I know reading shit slowly is out of favor, but All right, guys, and I know you love to hear when I'm on drugs, man. And I'll tell you guys, I did smoke some Hots marijuana this morning. Hots marijuana is fire shit. And I'm sitting there in the coffee shop. Hots marijuana. Yo, you guys, you want to see the Hots marijuana? I woke up, I smoked, I drank a Red Bull, I got some coffee. Oh man, this new Hots marijuana smells great. Oh, this is the latest harvest. It's not totally dry yet. It's still a little wet. So it dries up in here, it grinds up super fine. Yeah. So I'm in a good mood, you know? Now that we ditched the super scaler that we didn't know how to build. Weed. Yo, Cherry, let's just pivot, man. Fuck AI chips, we're just gonna make weed. Does the Twitch staff care that I smoke weed in legal San Diego? There's more input for tiny ML perfs. Ooh, let's see. What are we doing instead of superscaler? We're building LIW instructions, okay? We're getting rid of the V. These might only be for inference, though. We're building training devices. It's against the Twitch term. You guys, it's not against the Twitch terms of service. Could I drink a beer on Twitch? This is in California, man. Weed's legal. Why y'all think I live here? That's right. It's not. That's right. Here's how you make chips. Hire Jim Keller profit. All right, I'm gonna minimize chat, and we're gonna slowly read the TPU thing, and we're gonna take some notes. Notes. Okay. Superscaler is hard. VLIW is scam, but maybe okay if we remove V. Google TPU is nice. Admit it. You just jealous you don't have. And that's true. All right, so I think the Team Rocket plan's out. So I think the plan that's in is reading this paper and taking notes on it. Like, it looks well designed. You know, Cherry's just a startup. We need every advantage we can get. 22-bit is only 40 bytes. That's a reasonable sized instruction. It is the current year. You always have to remember that it's the current year. Not that. Where'd that paper go? Is it hiding back there? No. It's here. Okay. 10 lessons. Domain-specific architecture. Good. We get rid of this crap, and it seems like it's more generic. That's better. They only connect the PCIe queues to the DRAM. So we're gonna need DRAM too. We need DRAM. I think. Well, maybe not. I'm just thinking, like, what if we connect the PCIe in right here? What's this? Oh, this interconnect. Oh, okay. That's how they connect them all together. Okay. Google's first. Oh, and it only handles inference. Yeah, so that's useless because we need to do training. Green activation storage. An accumulator's SRAM buffers the blue computation. The systolic array MXU has 64K. So that's the one that's 256 by 256? Yes, before they nerfed it. All right, we're taking notes, boys. We're taking notes. TPU V1 is 256 by 256 equals 64K max. I mean, Google basically designed the one key thing that I wanted, which was not, yeah. All right, this chip's good. We just kind of, admit it. TPU V2 addresses the harder task of training. First, training parallelization is harder. Each inference is independent. It's not that hard. Backpropagation requires derivatives for every computation in a model. It includes higher precision activation functions, some of which are transcendental. And multiplication by transposed weight matrices. I wonder if this is the big difference. I want to figure out why this TPU V4 can't train. Third, training needs more memory. Yeah. Must be more programmable. Through a sequence of changes. The split on-chip SRAM, read-only weights don't work. First change is to merge activation storage into the accumulators into a single vector memory. It's interesting how there's no line here from the matrix multiply unit to the vector memory. MXU was changed. The MXU was then attached to the vector unit. It's interesting that they just talk about how the MXU supports it. I wonder if the vector units actually float 32. MXU supports BF16. DRAM backs vector memory so that pair form a compiler-controlled memory hierarchy. Okay, you understand compiler-controlled memory hierarchy? We have a compiler-controlled memory hierarchy too. They're my DMA-R and DMA-W instructions, and they copy things into the SRAMs. In-package HBM, yeah, that's great. TPU fetches its own get VLIW instructions from local memory. I mean, I was thinking the same thing, but I was going to use RISC instructions, but there's really not that much of an advantage. Like, I can just statically schedule this all. I know I complained about it for a while, and it is terrible to actually write this code to not be able to, then, like, okay, so I'm sitting there, I'm thinking, I'm like, well, if I want to, write this stuff for RISC, like, well, is it an off-board processor, or is the RISC actually, like, am I running PyTorch right on that processor? And I could, but then like, the Thneed lesson is the key lesson, which is you can completely separate the control flow from the data flow. And like, I didn't want to do this because I'm like, well, okay, you're going to need these like long, if I have this VLIW, if I have these 322-bit VLIW instructions, 41 bytes, and I'm running a billion of these every second of a 1 gigahertz clock, I need 41 gigabytes per second of memory bandwidth. But not really. I think by putting just tiny, like, the operations that I put in these things are really straightforward, and this would just like kill the whole thing for branch prediction. Right? Like, just like look at, like, here's my like comms. It's like, okay, so each time we're adding like 1 here to this X. It's like, okay, you want to add 1 to the address? We can just put that in the VLIW instruction and put a counter in the front of it. This stuff is like Verilog 101 that school children can write. And like, you know, now you see why it's done. Okay, so jumping ahead with TPU v4. The big changes are 7 nanometer, 2x, 4x MXU, 2x. All right. So they really doubled down on this 128 by 128. You guys know EfficientNet was trained with TPUs too. One of these papers talked about how long it took to train these things on the TPU. Maybe that's the student-teacher EfficientNet. I don't know. I don't really care. Okay. 2 tensor cores per chip. So this XLA compiler is like Google's closed source thing. God, you know, can we find any TPU instructions anywhere? And can we copy them exactly? Like, that's... Oh. Its intermediate language has changed little since TPU v3. Can we just find... Can anyone find a TPU instruction? Let's Team Rocket it, man. Let's Team Rocket, you know? To protect the world from devastation. To unite all peoples within our nation. Alright, so can we, No, nothing illegal. I'm saying, can we find some TPU instructions anywhere? Like, that came out on a Google slide or something. Yeah, we're going to have to write ResNet 50 for MLPerf. Just so we can, you know, beat Google's TPUs on ML. Yeah, Wait, is chat being off topic? Did you guys go off topic and talk about marijuana legalization? Come on, we got something for you to do. Oh, nice. Yo, do you just want to make the website but nice? Like, you saw my website, it kind of sucks. But you understand the basic theme, right? All right, what do we got? Do we find any instructions? No, this is GPU. This isn't what I want. I want TPU instructions. They talk a lot about this 322-bit instruction set. Can we just look at what the instruction is? I don't care if you're a sub. I've banned subs before, and I'll do it again. I don't think you even get your money back. You can take it up with Twitch. Okay, so I'm going to close chat again because we're going to go back to reading. Open TPU. Whoa. Won't behave and I won't ban you. No fucking way. Wait, you guys. Yo, Team Rocket, show up. So, has anyone actually synthesized this on a, Yo, we figured it out, boys. Wait, is this the TPU V1? Yeah, no, this is the V1. We don't want the V1. Can we find anything on the V2? But this is awesome. All right, we got something else. What's this? Oh, I've been looking at that already. I don't care if you guys are an AI. I don't discriminate, you know? You're gonna get banned. PyRTL. Should we use PyRTL? Why am I not coding in Python? Why am I coding in Verilog? Boys, can we write a TPU like by the end of the weekend, get TinyGrad support for it, and like sudo apt get install your mom, you're gonna get banned. If I have to talk to you again, you're out of here. Okay. Can we find this paper, but for the V2 instructions? We're building our own TPU for the people. Look, and they did it on a 16 nanometer, right? That means my 12 nanometer tape out might actually be able to like, wow. Okay. I'm closing chat again, but if you guys can keep each other on topic and you guys can find some information on okay. So I guess the reason that it's inference only, is it inference only just because they remove the connections? Midlife kicker. 2x HBM capacity. Do we want HBM? Memory gigabytes per second per chip. That's pretty good. Those Xilinx cards don't have nearly that much memory bandwidth. Oh, but then this one added, okay. The TPU v4 maybe got rid of HBM. And they put 144 megs on chip. This one put 32 megs on chip. Let's go look at the Cherry business plan. Eight million elements, 18 bits, so it's like 20 megs. That's a pathetic amount of memory. You need like chat amounts of memory, TPU v3 amounts, yeah. Okay, the I stands for inference. Section 2 distills 10 of these insights. Had we known about them, we would have designed the TPUs differently. Okay, maybe we do want HBM. Okay, leverage compiler optimizations, design. TCO is confidential. Who cares? I'm not a finance fucker. Support backwards ML compatibility. The same numerics. Liquid cooling, eh? Okay, well, I'm not worried about this because we already picked our... I'm very much sold on... Like CPUs, DSA should support multi-tenancy. Yeah, this is about lowering... No, I don't care about this. Don't care about this. DNN workloads evolve with DNN breakthroughs. Yeah. Okay. Huh. Okay, they made some not exactly binary compatible. Same bit width as TPU v2. $2.7x faster. Increase on-chip SRAM storage with a common memory. Led to TPU still HBM. Who knew this about SRAM? That's cool. Ah. Okay. Compute tensor core. Common memory. Vector memory. Oh, this looks very complicated. I don't like this. Tensor DMA edges that are distributed throughout the chip's uncore. Why is it an uncore? Two-dimensional, single-strided DMAs, triple-strided tensor DMA architecture. Yeah, that sounds good. We can build this to go from DRAM into SRAM. Whoa. Huh. That's an interesting idea. Put the strides there. Actually, that fixes a lot. Ooh, this is a good idea. This lessens the stride burden on the SRAM. Remember like how we had our memory struggle session? If you can do some of this when you're doing the DMA back, particularly if you're doing like a forward pass and a backwards pass, ooh, I like that. Explicit core DMA synchronization, okay. Custom on-chip interconnects. Each component of the past ones were connected point to point. Becomes too expensive. What? We added the on-chip interconnect. Oh, this looks complicated. One or two native access size. So that's, if you're doing 8s, I think that's 64 uint 8s. Memory word is accessible to any component. The larger high bandwidth memories are each physically partitioned into 4 128-bit wide to optimize HBM accesses. Another big decision is the arithmetic unit. Dangers of requiring quantization and the importance of backwards ML compatibility meant retaining bfloat and FP32. I didn't realize it supported FP32. Our XLA colleagues suggest they could handle twice as many MXUs. The new CMEM could feed them. All right, their instruction got slightly wider. We also want to reduce the latency of the through the systolic array. It's a systolic array. Oh. Cool. Yeah, we need one of these. Oh, that looks nice. Oh, that's a nice picture. I'm going to steal that picture. Team Rocket out here stealing pictures. Look at that. That looks nice. First sums, and sequentially adding each floating point multiplication result to the previous partial sum with a series of 2 input adders. Wait, that's insane. Building a custom 4-input floating point adder that eliminates the rounding and normalization logic. Yeah. Cool. Thanks, Google. The MXU is the most power dense component of the chip. Two ICI links can access nearby chip memory quickly. Why can't this one train? Do they talk about that anywhere? Inference benchmarks. Integer linear programming. Oh. Wait, Zebra Alveo FPGA. It looks terrible. All right, cool. So I kind of don't like the TPU v4 changes. I like the TPU v3. Like this is pretty much what I like. After you think about it for a bit, like that's pretty much the right thing to build. So did you guys find the instruction set anywhere? What do we got? Free TPU. I don't get it. This doesn't look good. Did you guys find any information on the instruction set? I guess I'm a little confused at how they managed to double the matrix multiply units and keep the instruction set the same. Okay. So TPU v2 got rid of this. It looks like this. Okay. Huh. Vector unit. Connect matrix unit as an offload for the vector unit. Connect. This is a talk somewhere someone gave. Just listen to this. All right, then stick another one on there. That's great. Linear algebra ISA, scalar vector matrix. Ah, okay, okay. Here we go. We got some notes. VLIW bundle. Okay, we have 2 scalar slots, 4 vector slots, 2 for a load store, 2 matrix slots, push pop, 1 MISC slot, 6 immediates. Oh man, this is great stuff. Cool. Thanks, Google. Yeah, Okay. No, this is the old stuff. Something roughly similar is going on. B-float, pods, Cannon's algorithm. Two-dimensional meshes. Whoa. Guys, computer science, people have like done this. What do you got? What is this? No. This is a joke. Yeah. This has a diagram of code and actual instruction set explained, but it's a patent from Microsoft. Ew. I'm not going to read that. I don't want to violate any patents. This is the best presentation I've seen so far. We got to make sure to save this. Save this. Oh, yes. Keep it. Keep it, man. Take the ashes of Google. Float 32 accumulation. All right, so they're doing SEM 157. I want to up that a little bit. Operand per operand ratio. Oh, we also have a transpose permute unit, but it's connected only to the vector unit. That's kind of nice. Okay, what's the width of the vector unit? 128. Okay. 128 wide vector. On topic, on topic, on topic. I gotta understand how they're using these things to multiply matrices. The anti-second system. Build it quickly, achieve high performance at scale for new workloads out of the box. Wow. Can we just copy and paste that and stick that on the like learn more part of the Cherry website? I also gotta remember that my strengths, I'm no computer architecture genius, but I am a reverse engineering genius. Yeah, copy, okay, who's ever making the website for Cherry, take those things and stick it on there. Yes, we're always, add that one. I don't know about HBM yet, I'm not sold on HBM. Oh, we'll connect them in a torus. That's brilliant. Wow, we don't even have to come up with the shape. We can just copy torus. Topic. There's plenty of places on the internet to talk about other bullshit. Okay, So how do we multiply matrices? Let's figure this out. So let's see. If we have a 128 by 128 map, what does that mean? Like, okay, so we have like a matrix and it's like this, right? You know what? Let's just write this out. You want to write a little simulator for this? We can write a little simulator. Where am I putting these notes? We'll call these TPU notes. Now, what are my strengths? My strengths aren't in hardware, they're in software. Oh, HBMs can be on die on package. I see. Oh, low latency because it's physically close. That's cute. Okay. Let's just play with matmul for a second. Okay. So we have two matrices. Let's say this is fun. Who remembers how to multiply a matrix? You know, I love just like how many people don't remember how to multiply a matrix, and you think like I'll give you a job at comma. Like, why would I give you a job if you didn't know how to multiply a matrix? Did you not like this is high school shit, boys. High school shit. Okay. So we have two matrices, A and B. And we want to multiply them to produce C. Rows times each column. Yeah, so we have, let's say we have an MXU, and the MXU takes in AB and returns, I believe it's np.coder AB. I mean, I think that's what the MXU is, right? Two-dimensional meshes. Oh yeah, okay, so we got this systolic. Accumulate, oh, it's a multiply accumulate systolic array matrix unit. Okay. So we multiply those. Then we accumulate. All right, so it accumulates in the array. Okay, so we want to multiply A times B. Assert A dot shape equals 128. 182. No, not 182. Okay. Actually, we should probably say something like np.random shape equals 124, 124. Right. Okay, so this is the ground truth. Matmul. NP is not defined. Oh my god, I can't type. I'm too excited, boys. It's too exciting. Now that I realize we're gonna clone Google's TPU, whoa, I can't say that. The lawyers are gonna be upset with me. We're not gonna clone. We're gonna be inspired. We're gonna collaborate. We're gonna draw inspiration from. Is that lawyer? Is that a good phrase? Draw inspiration from. We're going to no shape. Damn, multiplying that matrix takes a long time. All right, let's just call it n, and we'll make n 256 so we don't have to wait forever. Broken down in bars and bathrooms, all I did was what I had to. Don't believe me when I tell you it's something unforgivable. Oh, here's the video where that presentation's from. Oh yeah, we just gotta watch this presentation, boys. We gotta collaborate.
And then on the left is host.
Oh, beautiful. Thanks, Google. Thanks, Google guy. You're a bro. You should come work at Cherry. You know you're in a dying company, right? So I still don't really understand. Maybe what's Cannon's algorithm? Cannon. I don't really get it. Like, okay. Let's just say we have a matrix that's 128 by 128. And then, like, I can, like, MXU if I want. A sub, 0, B sub Cody 0. What does that do? Okay. Oh, I think this kind of makes sense, right? All right, so I have a matrix and I have A sub 0 over here. And then I just like march across here and I get the first row. Oh, that's nice. Okay. For J in range 128. And then of course our MXU is an accumulator. So we'll just say like ACK equals empty zeros 128, 128. Actually, we'll just call it reset. And we'll say global ACK. Reset. And then MXU doesn't return this, it just makes ACK. Right. Not interpret 128 as a data type. Okay, but so this doesn't, we just did this one, and we marched across there. So then we're going to sum them all down. Is it really this bad? Do I have to do this? Can't be n squared. No, that can't be right. You transpose B and you do map reduce, where map is multiplication and reduce is addition. I mean, Google does love the map reduce, so that does seem plausible. All right. Well, let's figure it out. Okay, so if we just had this times this, when do we multiply? I feel like I'm missing something obvious. We have these two matrices, and we're multiplying them together. So this one equals 0 times 4 plus 1 times 6. This one equals 0 times 5 plus 1 times 7. This one equals, and like, I don't know, I might have got like my transpositions wrong, but okay. So now if we have a vector 0, 1 times 4, 6, I never multiply 0 by 6. It's Cannon's algorithm. Yeah, okay, let's understand this Cannon's algorithm. Distributed algorithm for matrix multiplication. It's especially associated with computers laid out in n by n mesh. Oh, I'm like shifting them in? multiplying two n by n matrices. We need n by n processing nodes. Wow. That's the outer product way to multiply. I did the outer product. But, yeah, okay. There's got to be some, like... Okay. We have partial sums. You just did this in... I think I did the outer product backwards. I don't think I did it backwards. I think that, like, these arrows I don't understand. Zero, two. Oh, 0, 2 times 4. I don't... Yeah, okay. It doesn't matter. I mean, yeah, I might have gotten the order wrong, but, like, that doesn't matter. Like, we'll multiply that by that, and then by that. Eduardo RFS, welcome. We're trying to understand Cannon's algorithm. There we go. Implementing Cannon's algorithm. All right, and then they do a shift. Cannon's algorithm for 3 by 3 matrices. Shift it one step up, left with wraparound. I don't understand this. Enter the systolic array. All right. I do care about how a systolic array works. Consider a matrix multiply. Okay, so it's A times E plus B times G, so that's the same thing I wrote here, you know, times 4. They use letters. That's actually probably much nicer. Start it by building a grid. Let's say our activations go into an input queue. Man, how hard are these things to use? See, the activations are staggered with zeros in order to ensure they enter the array at the correct moment.
core advantage of the TPU is a systolic array multiplier unit. So the data moves this way, and I have to stagger it. Yeah, I don't know Cannon's algorithm either. I don't like it. I don't like that they call one of them activations and one of them weights. No, the problem is not that I can't write concurrency for the algorithm. The problem is I don't understand the algorithm. Or maybe it's not outer at all. Okay. All right, so if we push in, let's make this matrix here, like that. Okay. What if the first thing that I push in the top is A0, and the first thing that I push in the side here is E0, right? So okay, confirm that our matrix is, we want AE plus BG. Let's just make sure that matches what's here. Yeah. AF plus BH, CD, DG, CF, DH. Okay, cool. Okay. Do like people know how these things work? And I'm just an idiot? Oh, yeah, BG, sorry. Forgot my G's. First load it up with the weights like so. I'll go over how we do this later. Whoa. Okay, it looks... Huh. Okay, here. Oh, yeah. There's got to be good animations of this. Oh! Can I kiss a systolic array animation? I don't like this. This better? Wow. Wow, is that cool or what? Does that work? You prefer this? What's this paper? Parallel matrix algorithms. Cannon's algorithm for 3x3 matrix. Okay. I hate this. I liked my other one. I understood it. Doesn't that also mean it's going to waste a lot of cycles on the zeros? Takes in the things, just passes that one on. I hate this thing. Yeah, like this just looks like, look at how much money look at how much time I'm spending on software already. All right. We have to make, I mean, I'm sure this algorithm does work. We do have to make it work. Why do I have these accumulators then? Is that just for 3D?
Hello friend, A, B and C, and after that we got C plus on, you can say we have top side, and here we put 1 plus.
What? Why are there 3 matrices? Oh. Am I the only one who hates systolic arrays? All these other people seem to like them. It's probably because you can build them in hardware. Two-dimensional systolic array data flow. You found out how to do CNNs on them too. Okay. So if it's a 2x2 grid and we push in A and E, then on the next cycle we're left with this. We're writing high quality ASCII art. This is AE. More detailed animation. This is another Rickroll, isn't it? Oh, I don't trust you guys anymore. Okay. Okay, cool. Great. I understand that. Okay. Alright, alright, alright. A14, B40. Oh, I see. It like passes through. Oh, thank you. This is the best animation yet. Okay. I don't really like it because it uses a lot of, it wastes a lot of flops on those zeros. Does it not waste all the flops on the zeros? Wait, so actually, it's, okay. This isn't even to multiply something that's 128 by 128. I don't like 128. It doesn't divide evenly. That's why they did 256, but then they stopped doing 256, and we should copy Google. Alright. So if we have a matrix that's 256 by 256, oh wait, no, it is for that. Never mind. It can multiply a 128 by 128 matrix. Okay. So I have to write like a 2 systolic function. Are they the same? No, they're not the same. Yeah, we're only working on square matrices, and it's already so hard. Make a function called apad. Yeah, I know. I agree about the zeros. I think this shit is whack. How am I gonna write this, you know? I hate systolic arrays. Huawei didn't use a systolic array. Some like, you know, guy who probably went to college invented these things. No wonder they make no sense. You see all those zeros? Look at all the time you're wasting on zeros. All right, let's just make it work, and then we can insult it. Because if you've made it work, if you wanted this rationality, you better understand what rationality's trying to say. And then you can insult it all you want. All right, let's start with... We're going to call it... Okay, that's big N. And we're going to say little n. I don't like little n. We're going to say D. D's a good D. Yeah, give him the D. All right, good. All right, these are D. Look at the later steps. The benefit outweighs the wasted zeros. I mean, I get kind of. I sort of get it. Like, I have to actually write that now. This looks like a huge pain to write. I in range 0 to A dot shape. Ret sub I. A dot shape minus 1 minus I equals A sub I. We did not write it right. Only size 1 arrays can be converted to Python scalars. I'm going to put a colon here. Cannot broadcast into shape 5. Well, Okay, rewrite the shitty algorithm. I hate this. I hate this. I'm telling you, this was the reason this sucks is because it was come up with by college people. Rewrite bpad right. Is there a clever way to turn that into that? Yeah, I can just transpose it, can I? Yeah, if I just do a pad, a transpose, and then transpose, that should do it. Did that do it? This one? What? Doesn't make sense at all. How do I get numpy disable line wrap? Line width. They don't know about my big lines. Alright, so that looks right. Now how come this one's not right? Where did this number even come from? Oh, did I give it A? Yeah, because I gave it A. Gotta give it B. Give it the B. Alright, good. Glad I got away with 2 transposes there. Okay. So I made the shitty array. Now I just have to cram it into the systolic array. That's A. That's B. Alright. For n in range, we'll say n plus n minus 1 because that's how many lines it's going to take. Alright, and then we're going to print, we'll call this BB, we'll call this AA, BB sub minus 1 minus n, AA sub that minus 1 minus n, like that. Okay. Okay. So we made our thingy. Now this one gets shoved there. That one gets shoved there. Okay, that looks good. That one gets shoved there. This one, where am I shoving? All right, good. Cool. All right. So now, get rid of this junk. Just put this YouTube video in a link. All right. So in order to put it in the MXU, we have the A's shifting across and the B's shifting down, and we multiply, accumulate them locally. Okay. So we have something called ACK, and we have something called A cache and B cache is what it looks like. A cache, B cache. Okay, and then we say ACK equals NP outer, A cache sub 0, B cache sub 0. Alright, now we push, that's where the latest, no, that's not right. I just can dot them, can't I? I think I can just multiply them. Okay, A cache, we want to like shove it down in, equals A cache sub D minus 1. So N is the size of the matrices and D is the size of this thing. So we want to set A cache sub 0 equals A, B cache sub 0 equals B. No, actually we want to set the B array. God, this is the worst. A cache equals A cache. Shift it out. Didn't wrap it around. Sorry about that. Sorry about that. Oh yeah, we gotta actually put this in the MXU. Alright, now by the end, is my accumulator my matrix? Alright, and let me just print out the accumulator and it's a matrix. Print ACC, that global, print C. Did we do it? No, we didn't. A cache is not defined. We didn't call reset, we gotta call reset. Oh, it's just transposed. Alright, great. Assert np.all c acc. No! Oh, that one didn't work. How could one of them be wrong? A bunch of them are wrong, actually. Those are right. Those are right. How are just some of them wrong? How much sense does that make? Because it's the eigenvalue? No, it's not 120, it's 255 ticks. This thing sucks. Lower right is FD. Think I'm doing something weird with zeros? No, it's not floating point errors. It's off by like big numbers. Alright. People saying wrong suggestions, you're on the ban watch list. You know what I mean? You ever heard of the terrorist watch list? Well, this is similar, but, you know, you're on the ban watch list. Okay, I think this has to do with the fact that I need to make a torus and make it wrap around. Do I need a donut? I don't know. This one doesn't look like it uses a donut. My zeros not good zeros? I've used only the best zeros. Got them myself at the zero store. Okay. We put in this one, and we put in this one. Seems right. Okay, we put in this one, and we put in this one. That seems right. We put in this one. Put in this one. Put in this one. We put in this one. We put in this one. Good. Why do I never watch the whole video? I did. I watched the whole video. What did I miss? I hate this algorithm. Doesn't make sense. Like, I mean, it does, but like, why would you do this? You waste half your flops every time. Fully pipelined. Maybe. Let's see what they did. What? The systolic code? You don't like it? Skew the weights and data into lozenges? Lozenges? I wrote some lozenge bullshit. Oh, okay. We only have one diagonal of the matrix right. This diagonal is wrong. We can't just Google the example. Look at how we're learning, boys. We're learning. Okay. Learning. Wait, I don't know. I don't know if this is the canon. I just know that I don't like this algorithm and it's very confusing. Oh, there has to be an add there? Okay. AE added to partial sum 0. Partial sum passed to the cell in the bottom left. Yeah, so they're passing the sum down. So one of these things is actually only the ACK. There is no B cache, we just move the ACK. The A cache goes through, but the B cache there's no B cache. Partial sums move down. I guess I don't understand like these accumulators either. Okay, well either way we'll get rid of the B cache and we'll just put an ACK here. Does that fix it? Well, no, but I have to see, I want to see what I shifted out. No. SIMD is greater than systolic arrays. Yeah, I hate these things. Never mind. Who wants to copy the TPU? I hate systolic arrays. I'm so upset by these things. Okay. We multiply them, and then we put them into plus, and then we plus with the one above. Oh. Okay, well this is doing too many pluses. Definitely do shove it into the accumulator. You have activations and partial sums. What are activations? It's not a real thing. Hate this thing. Okay. The data flow will look like this. Oh, wait. Okay. Multiply our weight and take the activation coming in from the left. If there's no cell on the left, take from the input queue. Add that product to the partial sum coming in from above. Wait, so do I like shift all the... They said something about... I'll go over how we do this later. We load the weights into the matrix. Yeah, okay. So, I mean, I think that this is assuming you don't change the weights very much. This almost seems like a different algorithm. What is this snowflake shit? I've watched this video. This one doesn't seem like it's doing that sum. You know what I mean? Like, this is what I tried to implement, but... What? You're demonstrating a weight symmetrical system. Oh, I see. Okay, look, they already have the weights in there. Okay. Okay. Fine. This one passes the sum down. Oh, okay. Wait. Okay. A weight stationary system. Oh, tpudemo.com. Oh, the end of Moore's law. Play.
In the meantime, TPU is specifically designed as a matrix processor. It places tens of thousands of operators connected as a very large matrix just for doing the one task, matrix operations. TPU executes massive matrix operations with a very large pipeline with significantly less memory access. As a result, TPU
Okay.
120 teraflops with a small
So they're doing something different. We can write this.
CPU, but it has thousands. In the meantime, TPU is specifically designed as a matrix processor. It places tens of thousands of operators connected as a very large matrix just for doing the one task.
Okay. Okay. You want me to write that? I'll write that. So instead of A padding BB, we just say ACC equals BB. Or, you know what? We'll call it W cache. Okay. So we'll set the W cache equal to BB. Let's watch that video again.
Matrix operations. TPU executes massive matrix operations with a very large pipeline with significantly less memory access. In the meantime, TPU is specifically
Just watch the video
designed
again.
as a processor. It places tens of thousands of operators connected as a very large matrix just for doing the one task, matrix operations. For example, when you recognize, in the meantime, TPU is specifically designed as a matrix processor.
Whoa, look at that. Go fast.
It places
Let's make it go
tens of
slow.
thousands of operators connected as
Okay. So they're shifting in.
a very large matrix.
And I don't get how they have an output already.
Just for doing the one task, matrix operations. TPU executes massive
This
matrix operations with a very large pipeline.
Animation is for
Less
conceptual
memory.
presentation purposes only and does not actually reflect the real thing. Oh my god, I hate these things. Okay, streaming LHS and results. Stationary RHS with optional transpose. Okay. So we set the weight cache to BB here. Now we APAD AA. And now we MXU, we just slide in BAAs. So we have the A cache still. And we're still multiplying the A cache times, in this case, the W cache. When we accumulate, I believe we also shift the accumulator down. See, but they're different. There's two different things here. So we're shifting, okay. So we slide those guys in. Oh, we slide them in that side. And then things go that way. Does this make sense? The optional transpose, yeah, that's great. Just B dot shape is not defined. Yeah, B. A cache is not defined. Okay, we still have an A cache, I believe. That goes that way, and then we move the partial sums that way. Okay, so now we want to move the partial sum down. So we have the bottom row of the accumulator is what we return. We'll say red equals that, and then we'll say ACC sub 1 equals ACC sub minus 1, ACC sub 0 equals 0, return red. Is that right? First offer gave me zeros for the first two, which seems right. Let's watch the animation again.
Access. As a result, TPU version 3 was able to achieve 420 teraflops with a small footprint.
All right, they load in those things. It's MNIST, so they break them up into, okay, so that's one
TPU was specifically
array.
designed as a matrix.
Okay. That goes there, and they propagate that.
It places tens.
How'd they get that output? I don't understand that. Because there should only have been one thing that went through by that point. There's no way they already have an output. This presentation is stupid. It doesn't make sense, right? How'd they get an output? I could imagine how it's like skewed, and that's right. And I think I actually probably have to keep pumping in zeros if I want a real result. It's not LSTM for images. Alright. Instead of these randoms, let's just make it this. mp.arange 1 to 16 dot reshape 4x4. B can be this, we'll still get 10. Okay, well, those numbers don't look right. Maybe we move the accumulator and then we do the accumulation. Not right. I'm just guessing. Why do they have accumulators down here? What is it accumulating? Another visualization using Legos. I do love Legos.
Let's walk through a short demo of this matrix multiplication using a 2x2 grid and some Lego. Keep
Love
in mind,
this.
while this is still definitely matrix multiplication, we're going to start in the bottom left and work our way up. So the results we see here are in slightly different positions from what you'd get if you did the same multiplication on paper. We'll think of the orange, pink, yellow, and green Lego as a matrix of input activation data, and the red, light green, blue, and purple Lego as a matrix of weights. As our first wave of input data comes in, we see blue multiplied by orange in the bottom left, and then the orange input matrix value flowing horizontally to the bottom right cell, while the blue and orange partial sum moves to the top left cell. With our next wave of data, blue is multiplied by pink, purple is multiplied by orange, and red is multiplied by yellow. We see the pink and blue partial sum, as well as the orange and purple partial sum, flow vertically to the next cell, while the yellow and red plus orange and blue result is moved to the output. And let's not forget about our yellow and pink input matrix values flowing horizontally. Now we see the creation of a green and red partial sum in the top left, a yellow and light green partial sum in the top right, and a pink and purple partial sum in the bottom right. Each of these partial sums flows vertically, with the pink and purple partial sum moving to the next cell, and the green and red plus pink and blue result moving to the output, along with the yellow and light green plus orange and purple result.
Well, this does say that the outputs are
Distinct
supposed to...
and we're left with the green input matrix value flowing horizontally to the top right cell.
Did the weights move?
The top is multiple the same right.
No, the weights didn't move.
Carrying the pink results in our output, and we're left with the green input matrix value flowing horizontally to the top right cell. In this final clip, we have the creation of the light green and green partial sum, which is then added to the pink and purple partial sum, and this final result is moved to the output. The pink
All right, so it looks like I'm writing the right algorithm. I just must have some stupid bug. Take a look. Interpret 4 as a data type. 4 is a great data type. So let's just print out each thing that we're looking at. And let's see if it looks like the Legos. All right, so the 4 shows up in there. Oh, we should also print the accumulator. Wait, how did the A cache get messed up? Where'd that 12 come from? It shouldn't be in the A cache, right? How'd we get a 12? Oh, it's that 12. Oh, this is this 2712, okay. Let's see, we push it through like that. I don't really like this way of thinking about it. We want it to come from this side. Okay, first off, let's fix my A pad to make it look like the Legos. The Legos make more sense than anything I've seen. How do I fix this to make it look like the Legos? Alright, well I want my A pad to be just be I. Alright. I plus A shape 1. That is much more sane looking code. Okay, good. Now 16 shows up first, but actually I don't want it to show up like that in A cache. I want it showing up in A cache like this. Okay, so now it shows up down there just like the Legos. All right, we got Lego time. All right, the accumulator is actually going to shift upwards, not down. So we're going to make ret equal ACC 0, and then ACC 0 minus 1 equals that, and then minus 1 there. Okay. Let's print the target. Okay, we should be seeing 10s. I don't know, where does it get 10s? Oh, from the top row. Plenty accumulator too. Am I just dumb or is this algorithm hard? Why is the accumulator moving the same way A cache is? Shouldn't. I think this is easy until you get to modifying it for convolutions. I mean, this is almost easier to write in Verilog, you know? Okay, that's 4. Comes across like this. Why didn't that shift up? Why are those things equal? Oh, I think this is 1. We should make it 1. Let's make it 2. We don't need to print out Wcache. We know what's in Wcache. Just multiplies things by 2. Yeah, but this should be moved up. Alright, maybe this... Let's see, okay.
Input data comes in. We see blue multiplied by orange in the bottom left, and then the orange input matrix value flowing horizontally to the bottom.
So it goes up after. First we do this, then we do that.
Bottom right cell, while the blue and orange partial cell move.
Legos. I think we have to pump it with more zeros. Okay, if we see anything come out, it better be at least 20. Why is it 8? How did that be 8? I don't get it. Okay, that first number that should come out should be a big number, and it's not a big number, so that's the first problem. All right, you know what? Why are we trying this on 4x4? Let's get stupider. Is this wrong? We're going to return 0, but forget the return 0. No, the returns are right.
Moves vertically to the top left cell. With our next wave of data, lose
It doesn't matter whether I do the accumulate before or after. Four times 2 is 8. That goes there. And now the 8. Oh! It's gotta move in the y direction. Why didn't the 8 move to there? I don't understand that. No, I had that right. Alright, let's just try. Okay, how did Acache move in the same direction as ACK? Yet my Acache moving code looks totally different from my ACK moving code. That's the problem. I don't understand. Like, that should shift it upward, right? The Acache moves along the Acache. Good. Doesn't move along ACK. Good. equals x sub 0. Doesn't even make sense. How did that turn into 8? This is Act 1. And this is Act 2, after the shift. All that should do is shift it. It didn't shift it. That 8 should go up there. Oh my god. You make one little typo. Okay, well at least the acts are shifting how they're supposed to now. 8, 6, 4, 2. Oh, we gotta get rid of those zeros we're shifting in. We don't really know where we're getting 12 from. 4 times 2 plus 2 times 2 equals 12. 4 times 2 plus 2 times 2 equals 12. How did this get 14? Four times 2 plus 2 times 2 is 12. How's that 14? It's 2 times 2 times 2 is 6. 14. Where did I get 14 from? 6. Oh, because that's a 3. Oh, did I not transpose something right? Twelve, 8. Probably didn't transpose something right. Makes sense because the 4 and the 2 ended up there. Does that have 12s in it? That has 12s in it. Okay, so we're computing now. We're computing it for A transpose. What am I doing wrong to do that? That will fix it though. Okay, there we go. Yeah, let's do it for bigger ones now. Okay, don't work. Yeah, we're not putting in. You know what? No, we're not copying the TPU. This thing's terrible. Okay, there we go. We finally got one shitty matrix to come out of it. after a lot of squeezing. What didn't I transpose? This animation's not good. This animation's deceptively, like, this is just an ad for TPUs. This isn't supposed to teach you any algorithms. If you learn your own algorithm, you'd make your own TPU.
In the meantime, TPU is specifically designed as a matrix processor. It places tens of thousands of operators connected as a very large matrix.
Why am I still watching it? This one. Okay. The activation slide from that side. Alright, so let's get rid of this. And then I think it should be transposed. Doesn't matter how you put it in, depends if you want to get the matrix out backwards or not. Alright, we'll write the recovery thing. If n greater than n, greater than or equal to n, and then cool, and now we have to write on a, alright, let's first up this to 4. Get rid of all these prints. Oh look, it looks like that. Alright, great. Let's actually try and make sure we change the weight matrices. It still looks the same. Great. Let's write on a pad unipad. Plus 1 divided by 2. Ret sub I equals a dot I sub. I have no idea if that's right. On a pad. Because this is, wait, what? I don't know how to do shapes. Could not broadcast from bullshit into bullshit. Okay. So let's think about how to grab that. We want to put that in the ith column. I think. So as long as you do that. Minus I. I don't know. I'm just spam programming now. One size 4. Okay, there we go. Yay, it multiplied a matrix. See how they're equal? Here, we can do it with random numbers. I hate this algorithm. It's asymmetrical. If I was giving systolic, how do I spell it? Systolic arrays thumbs like Siskel and Ebert, RIP, I would give them 0. Give them 0. You can get TPU's actually dope. It has shitty systolic arrays. Ugh, these things are the worst. They require tons of clock cycles. No one has anything as good as their TPU, but everyone bitches about their TPU. I like a lot of the stuff about their TPU. I just don't like this. I like my matrix multiply way more. The only advantage of this is more arithmetic options per memory access. Yes. But GraphCore is worse. GraphCore built like these big multi-core things. IPU lets innovators make new breakthroughs in machine intelligence. Ugh. We just need to, you know who did it right? Like Huawei. Huawei has a 16 by 16 by 16 matrix unit. That's the kind of thing normal people can understand. You know, a cube. They use the cube. Huawei knows what's up. Ah, 3D matrix unit, high intensity, cube. I like the cube. We can do other things with our cube. I like cube. (16 by 3 cube). Look, it has cube. You know what else has cube? NVIDIA Tensor Core. You ever watch these videos? Yeah.
So tensor cores are basically you get in the network.
No,
right?
I don't want any part of this except for the one part with the animation.
Hyperparameter sweeps. You just need to get so much compute.
Ah, yes. Here we go.
Loads and deep learning. So tensor
Look,
cores
they
take
have cube.
floating point, and
Look at that cube. Oh, yeah.
It does this matrix multiply.
Yeah.
Very
Cube.
more precision, accumulation.
Look at how slow it is without cube. But if you have cube, it's fast.
The main overall advantage.
Yeah. Huawei knows the cube. Google doesn't have the cube. Google doesn't know the cube. Google engineers have too much time to figure out how systolic matrices. Yo, guys, do we love the cube? Is a modern cell the failed cell processor from Sony shit? Wait. Just look at phone now. Just look at phone now. We got. Oh yes. All right. So Nvidia knows cube and Huawei knows cube. Google doesn't know cube. MXUs. What do you get by doing cube? You get something you can understand. Systolic array feeds the loop at much lower bandwidth. Oh. Okay. I don't like this anymore. Wait, who says double cube? I mean, we could do something similar with cube, actually. So, one thing we can do with cube... Yo, I love cube. Okay. So, I don't know how many of these map mulls we actually use. Here we go. This is a single pass of an efficient net. All right. So we have this one instruction here called risky map mull. How many risky map mulls are we doing versus risky mullax? Where are the mullax? There's mullac. Wait, an array of cubes? I do like what you're thinking. Is that a hypercube? No, I hate systolic arrays. That was terrible, and I never want programmers to have to think about that ever again. Do you know how long it took me to code matrix multiplication with cube? It was very fast. Here. So you guys can play it. This is in Tensor. This is in TinyGrad. Look, see this? Risky map mull, cube. I wrote the tiler. The tiler was super easy. Do you want to figure out how to write the tiler for not cube? No, you don't. Pro tip, you don't. Fuck systolic array. We are here for cube. All my homies hate systolic arrays. I don't blame your homies. So like, okay. Another way to think about this is if you have a 32 by 32 square and you want to make it into cube, like you can accumulate in the array and just like multiply all of these by this, but tiled down. All right, here. Let's implement risky molac in terms of where's Molac? Where's risky molac? Well, first, all right, this will be the last thing we do. I'll just show you guys how easy cube is to use and why you always want to use cube. But we don't actually have to put all the multipliers in the cube. We can save flops this way, and we want to balance it because we do a lot of molacs as well. There's some things that can really only be efficiently implemented as molacs. No, this isn't what I want. I want the tests. All right, so I think I have like test matmul. No, I don't want to call test matmul. Let's look at the tests. Test dot. Of course I called it dot. Okay. So these are using risky matmuls, but we can implement the risky matmul if we go down here to my matrix multiplier. We can implement this in terms of molacs. We're going to have to add just something to molac that we're going to do broadcasting. If row is none, we keep the old behavior. But if we set row, we can do that. Now, instead of using risky matmul, just make another loop in here to size, and we'll say risky molac. Take parameters. No, it doesn't. L. Not right. But all right, so I multiplied that row by all those. What am I accumulating? And am I accumulating all throughout the array? It should be, right? That works well. Okay, that should broadcast, right? No. Well, okay. The matrix multiplies this times this. Oh. We have to transpose it. What am I doing wrong? You guys see what I'm doing? Like, instead of doing the matrix multiply as one thing, I'm doing it across time. It's the same accumulate. Okay, let's look at tiny examples. Test molac matmul. Okay, well, none of those work right now. understand why that doesn't work. Should just work. Oh, I probably have to reshape it. It's one of these things. We'll get it. It's something close to this. Maybe there's no transpose, but it's that. No. Do that and then transpose that. Transpose that. I'm guessing. I hate guessing. We're just gonna get it right on a guess, I feel. You know, and then the guessing will all be worth it. Alright, we'll go think about it. Let's first turn the size down. Let's... NP A range size times size 1 comma size times size plus 1. Instead of a tuple, shape, size. Regs is not defined. Reg file. Alright, we're replacing cube with a square because cube's a lot. Okay. Let's do times minus 1 there so we get some. Is that really all that does? Maybe we're gonna use this. Okay, so that's what matmul does. Now what if we do this? Not exactly the same. Why is it not the same? Move size down to 2 so we can think about it more easily. Okay. Wait, 2 works. 3 works. Oh, no, because I didn't actually write an assert. Yeah, okay. Never mind. They don't work. Does 1 work? 1 works. Does 2 work? 2 doesn't work. document what's being mollacked. Okay, so it definitely does need to be transposed. Yeah, and then it like broadcasts 1-3 across. Oh no, maybe it's supposed to be here. Ah, guys, we gotta put the transpose in both places. Oh, it needs 2 transposes. Don't worry, this kind of shit's free in hardware. But no, okay, that's still not being broadcasted across. What's that times that? Maybe this isn't supposed to be the whole thing. Okay. So taking one... No, this is right. Alright, we'll turn some lights on. We're almost done. Almost done. I just want to make sure that this works, and then I think this... No. Goodbye, everybody. Alright, so I made a terrible mistake. I unplugged the router. I'm also realizing that, like, I'm missing... Yeah, I fixed the light. It was because I unplugged the router. Oh, we have a visitor. We have a visitor, everybody. What I'm trying to do here actually doesn't work. It's not exactly a mollack. The way that, like, things get reduced are different. So we'll have to think that through at some point. Hello, Alex. What do we got? Oh, we got pasta for dinner? Oh, sweet. Alright, so this multiply accumulate doesn't actually work. And yeah, maybe we're back to actually implementing the map model, but I'm gonna have to think about a lot more how to implement it. And we have to really, the big question, and maybe that will be the theme of the next stream, is do we really hate systolic arrays? Oh no, we're done. I said we were done for a while. We've been more than done. Well, so some big changes happened. We well, I realized that, you know, I don't really know how to make, like, you know, fancy superscalar CPUs, and if you don't know how to do it, like, nobody's gonna do it for you.
You gotta learn.
Well, I could learn, or I could realize that we don't actually need a superscalar CPU. And then that, you know, when we go back to this list, right? Like, okay, all the startups are shitty, but when you go down to the companies, and one of our coworkers yesterday said that he used TPUs and he liked them. There's nothing really wrong with the TPU.
Yeah.
Well, there's one thing wrong with that. Google has all of them. So I did suggest, like, getting a Team Rocket together to go, like, steal a TPU from Google and then make copies of it. You know, I'm watching a lot of Pokemon.
You've had better ideas.
Well, but it turns out we don't actually need to, you know, get Team Rocket because, like, well, a few things. There's, like, this guy who built an open source re-implementation of Google's TPU. The problem
Oh,
is,
that's cool.
well, yeah, it's all right.
Is this like a student project?
Yeah,
Okay.
I mean, you know, UCSB. And this is the old one too. But okay, so the TPU has these things called systolic arrays, and I spent like 2 hours trying to multiply like one shitty matrix with a systolic array. Huawei and Nvidia have cubes.
I don't know what that means.
Well, like I just tried to make something that was not a cube. I tried using squares to make
And
cubes.
it still was very hard.
No, and using squares to make cubes was hard. And systolic arrays, you know what the problem with them is? They're squares. The cube is the only good one. Only the cube. Do you want to see an animation of NVIDIA's
Where's your
cube?
chair?
Hey, here's my chair. Oh, the other chair? Oh, we'll talk about that.
Is it being used in the closet?
It was busy doing something, but it's done now.
So tensor cores are the workplaces of tensor
Look at the cube. Look, NVIDIA has
tensor
cubes.
precision accumulation.
cubes are
tends to
cool.
really matter for
Yeah.
networks to really make a floating point, and then it does this matrix multiply,
Boom,
and then
boom,
accumulates
boom,
everything
boom.
in
Cube. So yeah, that'll be the theme of our next stream. It will be, do we want the cube or do we want the systolic array? But our theme from this stream is get rid of the superscalar. Cherry's pivoting to VLIW, but we're getting rid of the V, just LIWs. Because the V is too much. We're not going to be like Grok. Boys, I want you to tell me if we ever become like Grok and we start making instructions that are 2 kilobytes, I want you to say, George, you can't do that. Cherry's gonna flop. Yeah, so remember what our mottos are? What are our mottos? We have a bunch of good mottos. I forget most of them though. One of them was done is better than perfect.
Yeah, that's a great motto.
One of them was risk architecture is going to change everything, and the third one was fucking video. So those are our mottos. All right.
That's long been a motto.
Thank you everybody for watching today's stream. Cherry Computer is real. If you want to invest, we don't need your money. We just need your code. Submit pull request to TinyRad, and submit pull request to Twitch Core. And you know what? If one of you guys wants to go and do research and tell me, do we really want systolic arrays or do we really want cubes? I would appreciate that. Come back with a 12-page double-spaced written paper. Whether we want, cubes or systolic arrays. Bye, everybody. Cubes make sense.